In this class, we see some examples on groups. Show that the set G is equal to set of all the matrices of the elements cos theta minus sin theta cos theta, where theta is a real number, is a group under matrix multiplication. Is it commutative? Here in this set, I am taking 2 by 2 matrices of the type, this type. Here this is element cos theta and this is minus sin theta and this is sin theta, this is cos theta. First row, first column, first row, second column, second row, first column and second row, second column. These two are the same cos theta, but these two are the same with the opposite sign. This is plus sign and this is minus sign, where theta is a real number. We have to show that this set G is a group with respect to multiplication of matrices and there is a tag. Is it commutative? So we go to the solution. I am taking a set A alpha. Here this matrix contains alpha, 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 alpha. So I will denote this by the symbol A alpha. And here I am taking cos beta minus sin beta, cos beta. And I will denote this by A beta. Here these two are elements of G, the set G here. A alpha is an element of G and A beta is an element of G. These two are any two elements in the set G. I am multiplying this. A alpha into A beta is equal to writing the matrix cos alpha minus sin alpha, cos beta minus sin beta, cos beta. On multiplication, I will get cos alpha, cos beta minus sin alpha, sin beta. And this is minus cos alpha, sin beta minus sin alpha, cos beta. And this is sin alpha cos beta plus cos alpha sin beta, and the last second row second column. This is minus sin alpha sin beta plus cos alpha. Using the trigonometric laws, I will write this as cos alpha plus beta and this as minus of, taking minus common, I will write minus of sin alpha plus beta. And this is sin alpha plus beta and this is cos of alpha plus beta. Here this matrix can be denoted by the capital A suffix alpha plus beta. So this element belongs to G. Here in all the four places it is a number, real number alpha plus beta here. So this is in the format mentioned in the set G. So this element is denoted by A suffix alpha plus beta and this belongs to set G. So closure property satisfied. Operating these two elements, we get element in the set G. Therefore, G is closed with respect to multiplication of matrices. Next, we go to the associative law. I will take three elements A alpha, A beta, A gamma in the set G. On the left side part, I will write bracket A alpha, A beta, A gamma is equal to. As in the closure property, I will write this as A alpha plus beta into A gamma. Again applying a closure property, I will write A bracket alpha plus beta plus gamma. This is equal to, we can write A alpha plus beta plus gamma. And on the right side, I can write A alpha bracket A beta A gamma. First applying this closure property here for this A alpha A beta plus gamma. This is equal to A alpha bracket alpha plus bracket beta plus gamma. This gives A alpha plus beta plus gamma. These two are equal. Therefore, these two are equal. Therefore, associative law holds good in G. Next, we go to the identity element. Let A alpha belong to G. Consider A suffix 0 belongs to G. Then A alpha A0 is equal to, as in the closure property, you can write A alpha plus 0. This gives AA. And again, A0 is multiplied with AA. We get A0 plus A and this is equal to AA. Here A0 is multiplied with AA on the right side and on the left side we get the same element AA. So A0 is called identity element in G. So we go to the set G here. Here I am taking 0 in the place of theta. So this cos 0 minus sin 0, cos 0. And we know that cos 0 is 1 and sin 0 is 0 and sin 0 is 0 and cos 0 is 1. So we get here 1, 0, 0, 1. In the theory of matrices, it is called unit matrix. 1 0 0 1 is called unit matrix. So thus we have this A0, that is 1 0 0 1 is unity element or identity element in the set G. Therefore A0 is the identity element in the set G. Next, we go to inverse. Let A alpha belong to G. Alpha is a real number, so minus alpha is also a real number. So the matrix A minus alpha belongs to set G. Alpha is a real number, so minus alpha is also a real number. So we can say A minus alpha is an element of the set G. A alpha is operated with A minus alpha. A alpha into A minus alpha is equal to A alpha minus alpha is equal to A0. And on the left side, A minus alpha, A alpha is equal to A minus alpha plus alpha is equal to A0. A alpha is multiplied with A minus alpha. This gives A alpha minus alpha and this is equal to A0. And A minus alpha is multiplied with A alpha, we get A0. That means A minus alpha is multiplied with A alpha. On the right side, on the left side, we get the same. We get the element A0. So, inverse element property is verified here. Therefore, we say that A minus alpha is the inverse of A alpha in G. Here we are taking any element of G. So, inverse element exists for each element of G. So, 4 postulates of the definition of the group satisfied here. Therefore, we say that G is a group with respect to multiplication of matrices. In the problem, there is a tag. Is it commutative? Let us check. Let us take any two elements A alpha, A beta and the set G. A alpha and A beta is equal to A alpha plus beta is equal to, we can write A beta plus alpha because alpha beta are real numbers. Real numbers are commutative with respect to addition. Therefore, we can write alpha plus beta as beta plus alpha. Thus, A alpha plus beta is equal to A beta plus alpha. Again, using the closure property, we can write this A beta into A alpha. Thus, A alpha into A beta is equal to A beta into A alpha. This is called commutative law. Therefore, commutative law holds good in G. Hence, G is commutative group with respect to multiplication of matrices. Here, I have taken a set G, a particular type of matrices. Cos theta minus sin theta, cos theta, where theta is the real numbers. Theta is a real number. I have shown that this set G is a commutative group. In the last problem also, we have seen that in general, multiplication of matrices is not commutative. But here in this set G, multiplication of matrices is commutative. So thus, it is a particular case where multiplication of matrices is commutative. Next, we see one more problem here. Prove that the set Z of all integers forms an abelian group with respect to the operation defined by A circle B is equal to A plus B plus 2 for all A belong to G. Here I am taking a set Z, that means set of all integers, positive integers, negative integers, including 0. I am defining a binary operation like this. A circle B is equal to A plus B plus 2 for all A belong to G. And show that this is the set with this binary operation forms an abelian group. That means you have to verify all the 5 axioms, 5 postulates or 5 conditions of the definition of the group. We go to the formal way. Solution. Let AB belong to Z, then A circle B is equal to A plus B plus 2. This element belongs to Z because A is an integer, B is an integer, 2 is an integer. So, sum of the addition of 3 integers is again integer. So, this belongs to Z. That means A circle B belongs to belongs to Z. Here A, B has A and B, 2 elements operated and the result belongs to the same set Z. That means closure property is verified, satisfied. Thus, Z is closed with respect to the binary operation circle. Next, we go to the associative law. That A, B, C belong to Z. Then, left side part, bracket A circle B circle C is equal to, we can write A plus B plus 2 circle C. Again, operating these 2 elements, we write A plus B plus 2 plus C plus 2. And I will write A plus B plus C plus 4 because Addition of integers is commutative. So we can take this to this part here. I will write 2 plus c as c plus 2. So we get a plus b plus c plus 4. On the right side, a circle b circle c is equal to, I will write a circle b plus c plus 2. And this we can write a plus b plus c plus 2 plus 2. So we get a plus b plus c plus 4. These two are equal. Therefore, these two are equal. These two are. Therefore, I will write bracket a circle b circle c is equal to a circle bracket b circle c. Thus, associated law holds good in Z with respect to the binary operation circle. Using this binary operation, we can guess the identity element. So, I am taking minus 2 here. That a belongs to Z and minus 2 is an integer. I am taking this minus 2. Operating this minus 2 with a circle minus 2 is equal to, by the definition, I will write a minus 2 plus 2, this gives a. And on the left side, minus 2 circle a is equal to minus 2 plus a plus 2 is equal to a. Here minus 2 is operated with a from right side and from left side we get the same a. Therefore, we say that minus 2 is the identity element in the set Z with respect to the binary operation circle. Remember this point here. Here binary operation is defined other way. So, I will write minus 2 is the identity element in the Z with respect to the binary operation circle defined in this problem. Next, we go to the inverse. From the definition of the binary operation, we can imagine this inverse element of A. Let A be an element of Z. Then minus A minus 4 is also an integer. Take minus A minus 4. Operating with A circle bracket minus A minus 4 is equal to, by the definition we write A minus 4 plus 2. This gives minus 2. And operating from left side, minus A minus 4 circle A is equal to minus A minus 4 plus A plus 2. And A is cancelled. 1 here 2 is cancelled. We get to minus 2. So operating minus A minus 4 with A from right side and from left side, we get the identity element minus 2. Therefore, minus A minus 4 is the inverse of A in Z with respect to the binary operation circle. So, 4 axioms of the group verified here. But in the problem, it is asked so that it is an abelian group. So, we go to the fifth property. Let A be belong to Z. Then A circle B is equal to A plus B plus 2. Here A, B, 2 are integers. We know that addition of integers is commutative. So, we can write this as B plus A plus 2 and this can be written as B circle A. Therefore, commutative law holds good in Z with respect to the binary operation circle. Here we got A circle B is equal to B circle A. Therefore, commutative law holds good in Z with respect to the binary operation circle. So, all the 5 axioms or 5 postulates or 5 conditions verified with respect to the definition of group. So, we can say Z comma circle is a commutative group. Here, we are defining a binary operation on the set Z of all integers some other way. We know that already there is an addition, but here we have defined some other problem, some other binary operation. A circle B is equal to A plus B plus 2. This is one problem here.